of how to do it prior to doing it with a calculator. So
Mhm.
I was doing one of the homework questions where it asked you to find the quartile 1, quartile 3, right?
Okay.
And then it was one of those ones where you had when the median, you had to add 2 and then divide them in half, right?
Gotcha. Okay.
So I was under the assumption that neither of those counted in that when you're trying to find the upper or lower quartiles.
Ah, okay. Well, they do. So can I pretend I put in some data here just to make it happen? So 1, 2, 3, 4, 5, 6. So you would have 2 numbers right in the middle, and the median part you said exactly as it should be is 7. Now, when you have 2 numbers in the middle, what you got to imagine is that the data gets split that way. So the 6 belongs to the little guy and the 8 belongs to the big guy. Now,
okay.
when we had a situation, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. When we had a situation where the middle guy was on his own, that one died, and these would be the little guys and these would be the big guys.
Okay, that makes more sense.
Okay.
Because some of the couple of the questions I was off by like a 0.5 from the actual
and
answer.
that would be the reason.
Yeah.
Yeah, that would be the reason. Okay, that was a good question. Beatrice, it looks like you were going to ask a question, then James beat you to it. What was your question going to be?
No, I wasn't going to ask a question. I was just looking at my camera to see if my dog could be seen in the back of my camera.
I can see a little furry thing, so I'm assuming that is your dog.
Yeah, he is. I was making sure I was muted because he's snoring pretty well.
Oh, that's cute. Okay, well, let's get started, everyone. Today we're going to be focusing on what Chapter 2, bell-shaped data, but there's some little tidying up I want to do on one of the earlier ones. So if I can just zoom over to this side here. Here is a very small data set, right? And we're going to find the median, we're going to find Q1, Q3, the interquartile range. And they called the guys, I think I've called them the upper fence and the lower fence, right? This is just another name for them. They're going to call them the lower boundary and the upper boundary. And once you know these two guys, you can then do this fella here, is it an outlier or not? So since that would take a fair amount of time, I'm just going to put in the key so that we can use the numbers for this question. WebAssign randomizes the question, so the chances are you won't get the same numbers anyway, so it won't matter too much. Let's see if I can find that question. Yes, I think it's this one, right? So for this set of data, the median is 10. This is Q1, this is Q3. The interquartile range is what you get when you take one away from the other. What I would call the lower fence and the upper fence, they're going to call it the lower boundary and the upper boundary. It's just a name. Now, when you look at the number 41, isn't it outside the biggest number, right? It's bigger than 34, which is why they said, yes, it's an outlier. Are we comfortable with that? So it's just a language thing. Upper boundary and lower boundary is just another name for upper fence and lower fence. And to remind you how you would calculate that one, this one here, the lower one would be Q1 take away 1.5 interquartile ranges. And this guy here, anybody want to tell me what's the formula for getting the upper fence, or as they call it, upper boundary?
So it's Q3 plus 1.5 IQR or entire quarter range.
Yeah, that's the guy. And pretty straightforward, right? Right, so we have covered that stuff, even if it's not maybe covered with the name that you were used to. Sometimes that happens in statistics, that there are more than one name for the same idea. So let's begin. with our new chapter, our new section from chapter 2, bell-shaped data. It is very common that when you collect a lot of data, and so imagine along here is the value, maybe the ages of people, and you go to your town and you collect lots, maybe hundreds, perhaps even thousands of people, and you will find that the data looks like this. Technically, it's lots of little rectangles, but the rectangles are so close to each other that we kind of abbreviate it with a nice curve. So when you see a single hill like that, the name, and actually there's lots of names for it, so here's the one that they're using right now. We call this bell-shaped data. And people's ages tend to look like that. Do you know if you find out how much money people are worth? Aren't the very rich over here and the very poor over here, but the vast majority are in the middle, right? Heights. Most people are in this range, but there are some very small people because they're very young or whatever, and some very tall basketball players or whatever, right? And so this shape is so common that, and we notice it happening a lot when we collect data, that it gets its own name. And that's the one that they're using today, and that's fine. But I want to give you some other names, because if you look up a video or you see something else, they may use this term instead. It's called a normal distribution. So if you see, oh, the data has a normal distribution, well, you just say, oh, it's a bell-shaped data, right? Or vice versa. I kind of like the name bell-shaped. I mean, it kind of looks like a bell, doesn't it? You know, if I do that, which I'm not very artistic there, does that look like a very badly drawn bell? Right? It does look kind of like a bell, so bell-shape's a good name for it. Okay. Now, we are still working on numerical summaries as well. And so I'm going to pick a very small data set. 1, 2, 3, 4, 5 numbers. And we're going to calculate two things. One is called the mean, which is very often written like that, and the new guy. And the new guy is called standard deviation. And the standard deviation is typically written as S. S for standard, right? Standard deviation. But you will see it as S with a little X, and you will see it sometimes as SD. Well, you realize that they're the same guy, that just some textbooks use one thing. So you might watch a video and the guy starts calling it this, or the guy calls it that, or whatever, right? We're going to use, I believe, S, because that's what WebAssign uses. Now, the mean, you already know the mean. If I was going to write that down, you would just add up all the numbers and divide by how many there were. 17, 32, 42, 49, 50, 60, 70. And I got really lucky there. The mean is 14. And right, it's 14, that's what it is. The standard deviation is the first guy that we've met where I can't really show you how to do it by hand. I could technically show you how to do it by hand, but nobody in their right mind would ever do a standard deviation by hand from scratch. It's ugly, it's messy, it's long. So you are just going to have to trust that you will do it on your calculator, right? Or later on, Salt, right? The program in WebAssign will do it for you. So let's show you how you get this guy called standard deviation. Oh, and by the way, standard deviation is another number that measures spread. It measures how spread out the data is. The only other guy that you know that does this job is called the interquartile range, right? Remember the interquartile range was a number to tell you how spread out something is, right? Standard deviation is a different number that kind of does the same job. So first things first, I am going to nip over and do this on our calculator. And the good news is you already know how to do it because you've used the calculator to get the 5-figure summary. Remember doing it for 5-figure summaries? The number you want is in that same place. So you hit start first, edit one, and you put in the numbers 3 and 14 and 15 and 17 and finally 21. So if someone says to you, find the standard deviation, you will go to your TI-85, 84. If you've got another calculator, then that's great. You'd have to find out where that is stored, but it does work. So remind you what you did. You do stats, edit, type in your numbers. Then you go start again. You move across to Calc 1. You press enter. And in my calculator, you press enter a few times more. And here we go. Do you see the mean is 14? Already did that by hand. X bar 14. Now, as you scroll down, do you see that there's a guy with an X next to it? Do you see that S of X guy? So on the TI-84, the standard deviation is called S little x, which is fine. And I'm just writing the answer down to 2 decimal places. So that's 6.71. So do you feel comfortable that if you needed to find the standard deviation and you've got a TI-84 or at least some software that you can do online emulators of it, that you'd be able to do that? You feel good about that? Right. Remember what I said, you can borrow a TI-84 off the college and where was I going with this? It won't cost you anything and it's pretty easy to do. Are there any questions so far? Does this seem, yeah, okay, plug the numbers in. I know how to get the mean. Now you've told me that there's a new guy in town called the standard deviation. And in this case, these numbers are spread out about 6. And you might wonder, and we'll talk about later, what does that 6 tell me? And it actually tells us an awful lot more than you might suspect.
That was my question right there.
What does it tell you?
Yeah, well, so when I was in the Navy, we drove small boats. Depending on what region you was in, you had standard deviation. So if you needed to plot a course to 200, your deviation for that area was 1.2. You would have to drive, 198.8 to get where you need to be. So
right.
that's
okay.
Yeah.
So if you were 1 degree out, you had to drive 1 degree away from it so that it would swing back in, right?
Yeah, exactly. So you'd end up where you need to be.
Yeah. And the phrase that they are using there is not our kind of deviation. It uses the same word, but it's a different thing.
Okay.
Well, actually, as soon as I open up my page here, because I'm kind of running around here trying to figure out where the heck I am. Here we are, bell-shaped there. I just want to give you an example of the warm-up questions, and then we'll talk more about what does this number tell us. And so I'll do a stop, and I'll zoom over just to show you the kinds of questions that you're going to get. Now, here is your data set. I better take the answers off, that's distracting now. Right. Here is your data set. Plug it into your TI-84, tell me the mean, tell me the standard deviation. So for these questions here, you're only calculating what they ask you to calculate, right? In this case here, you see that the data is just put in the form of a table, but it doesn't really change anything majorly, right? So I'm going to do that as my example. So in question 3, The data is 112, 121, 134, 155, make sure they don't skip anybody, 129, 117, 103, and 120. And we're being asked to find three things. The mean, we've already talked about him. The standard deviation. Again, we've talked a little bit about that. And a new guy called variance. And that's the guy that I want to kind of dwell on. So, for my data set that you probably can't see anymore, but right, are you looking at the emulator, the TI-84 emulator right now?
Yes, sir.
Okay, so I'm going to take that list of numbers and I'm going to find the mean and standard deviation as we always would. And then I'll talk about this third guy called variance. So I'm going to go start, I'm going to go edit, and I got lucky, all my numbers are gone, but if they weren't, I'd delete them. 112, enter, 121, enter, 134, enter, 155, enter, 129, enter, 117, 103, and last but not least, 120. And then I do start, I move over to calc, one variable starts as always. In my case, just hit a lot of enters, and the mean is 123.875. The standard deviation is 15 point, well, they want 3 decimal places, so 15.788. And if we scroll, there is no sign of this guy called variance. So let me show you how you get him. Variance is called S squared, which is kind of helpful because it means you take the standard deviation and you square it. So the variance is just the square of the standard deviation. So I can simply go to my calculator, take in that number and square it. And so I have 15.788 squared. And rounding off the answer to 3 decimal places, our final guy is going to be 249.261 if you round it off. So we have mean, calculator, standard deviation, calculator, variance, square that guy. So the last one you won't get directly, won't you just have to take this number and multiply it by itself? So if they ask you for variance, they don't always, but if they do, that's how you would calculate it. So far, so good. Now, imagine I have the numbers 1, 3, 7, a whole load of other numbers, 81, 87, 91. Maybe there's, 50 numbers there. There is a guy called range, and he is the maximum, the biggest number, take away the minimum, the smallest number. So in this case, 91, take away 1, gets you 90. There is a formula for getting the approximate value of the standard deviation. So we're not talking about a really accurate answer, but it's an approximate one. Can you imagine that this list wasn't 50 numbers, but 500 numbers? Do you really want to type 500 numbers into your TI-84 just to get the standard deviation? If all you really want to know is roughly what is it equal to, I don't care if I'm a little bit out. Wouldn't it be nicer if there was a shortcut, right? And the formula for getting the approximate value of the standard deviation is the range divided by 6. Now, the range is easy because can't you at least find the biggest and smallest number, right? The start and the finish. And so the range is 90 divided by 6. And so the standard deviation is 5. I think there's a couple of questions where you do that. So let's talk about what does the standard deviation tell us, right? We've got to that point where we can do it. Let's suppose that I have some data on the ages of students at some college, right? So I've collected a big sample of 200 or 300 students and I've got their ages. And I've done all the hard work and their average age is 21. And their standard deviation is 5. If this data is approximately bell-shaped, and it doesn't need to be perfect. To be bell-shaped, don't you just basically need to be one hill, right? If you're approximately bell-shaped, then here's a fancy expression. The empirical rule tells us the following. "68% of the data," so in this case, 68% of the students will have an age in the range of 21 take away 5 up to 21 add 5. In other words, if you take the mean and add and subtract one standard deviation, so on this side you will get 16 up to 26. So I can tell you that 68% of the students at this college are aged 16 to 26. Even if you never told me the original data, if the only thing you said to me is, I collected a lot of data on students' ages, and the average age was 21, and the standard deviation was 5, and it's roughly a bell-shaped, the empirical rule says that 68% of the data is within one standard deviation. Now, 95% of the data is within 2 standard deviations. So let's see what that looks like. You take the mean and you take away 2 standard deviations. So that's 21 take away 10, that's 11. And you go up to 21, add 10, up to 31. So I can tell you that 95% of the students are somewhere between 11 and 31. Interesting college list. And maybe they have some kind of after school activity where young people come. And then there's one more with the even weirder value that 99.7% of the data is within 3 standard deviations. So if you took the mean and you add and subtract 3 standard deviations, you would get 21, give or take 3 lots of 5. You get 21 plus or minus 15. At the lower end, it would be 6 up to 36. That'd be a really weird college. And we call that the empirical rule, which means all I need to know about any group of people is tell me their mean, tell me their standard deviation, and tell me that it's approximately bell-shaped. And I can tell you tons of things about those people. I'm going to visualize it for the next one. There's a very common IQ test. And the average IQ people, adults, is 100. And the standard deviation is 10. Right? And IQs are pretty much bell-shaped. If I draw a number line and I put right in the middle 100, and I add 1 standard deviation, then a second standard deviation, and then a third. And if I go and I take away 1 standard deviation, I take away 2 standard deviations, and then finally I take away a third standard deviation, I can visualize the same information I gave, but to me, pictures make things much easier. In this range here, you will get 68% of everybody who took an IQ test. If you move to 2 standard deviations, which is here to here, you go from here to here, you are now looking at 95% of the people who take IQ tests would be in that range. They'd have an IQ from 80 to 120. And then lastly, from here to here, anybody whose IQ is between 70 and 130, 99.7% of all the people who took an IQ test will have a score from 70 to 130. We now have another way of figuring out if someone is an outlier, because outliers live here. So if your IQ is greater than 130, won't you be an extremely unusual big number, right? 99.7% of the people don't have that kind of IQ, right? You are really rare. You are really rare and really big. You are an outlier. And down here, you might have an IQ of, I don't know, 60, 65, whatever it might be. Those people on this side are also outliers. So the outliers are the ones that are furthest away, right? The furthest at each extreme. Now, when you talk about people who are outliers on this side, won't we call them geniuses, probably, right? The Einsteins of the world with huge, massive IQs that very few people have. And on this side, won't we call them football players? Oh, come on. That was a good joke. Football players, right? No? Yeah, it's the best I can do. Okay, I'm going to give you a joke then, because I need a joke. This student came to college every exam, only in the exams, with all his Seahawks stuff on, right? His Seahawks t-shirt, his Seahawks baseball bat, you name it. If it had a Seahawks on it, he had it, right? Seahawks ring, the lot. Only for exams. And finally, his friends just got so curious. He says, look, I've got to ask you. He says, why do you take your Seahawks stuff with you during exams? And he said, well, I know I'm always going to pass, even if I shouldn't. James, you are shaking your head. Do you not get that joke?
I do. I do.
Is it still too soon?
No, I'm not a Seahawks fan, so.
Oh, so you can enjoy that one.
Oh, absolutely.
Okay. Okay, are we comfortable with this new guy called the empirical rule, which says if it's normal, bell-shaped, and you tell me the mean and standard deviation, I can pretty much tell you a range of values where 68% of the people will be, another different range where 95%, a third final range where 99.7 are, and anybody who's left over is an outlier. And that is pretty powerful because I only need to know two numbers, right? The mean and standard deviation, and that it's bell-shaped, right? And with that in check, pretty powerful. So I'm now going to show you how WebAssign kind of asks that question, because sometimes they ask it in a way that might not at first sight seem so obvious to you. Okay. Scores in this particular IQ test are bell-shaped. The mean is 100, and the standard deviation in this test is 15, right? So I'm going to build one of those little pictures I've got. Now, the only difference is they put a little hat on it. Right in the middle, D, you see it right in the middle? That's going to be the average, which in this case, the mean is 100. Gotcha. Now, if you move one standard deviation to the left and one standard deviation to the right, in this case, 15, you're going to get to what on this side, 85, and on this side, 115. So far, so good. Now, 68% of the people are within one standard deviation, so 85 to 115. Do you see how I got those two numbers? Middle, one to the left, one to the right. Now, if you want to go to B, that's 2 standard deviations, right? So imagine you start at 100 and you go 30 to the left, which is 2 standard deviations, and 30 to the right. So you'd go what, to 70 on this side and 130 on that side. And if you do 2 standard deviations, you get 95% of the people. So that would be from 70 to 130. Now, if you do the final one, which is from the center, 1, 2, 3 standard deviations and 1, 2, 3 the other side, you're going to basically be doing what, 3 lots of that, 45, right? 45 to the left, 45 to the right. So 45 to the left makes that 55, 45 to the right makes that 145. And so people who have an IQ from 55 to 145 make up 99.7% of all IQs that you're likely to get. Okay, so far so good. Now, I would have loved them to put in a question like, is an IQ, so I'm going to do it, is an IQ of 150 an outlier? Yes or no?
Yes.
Yeah, it's an outlier because isn't it bigger than that guy?
Mhm.
Would 82 be an outlier?
Yes.
Oh, look there.
Oh, yeah,
82,
you're right.
Yeah, you're looking up here, but you should really look at the last one, shouldn't you?
Yeah.
So 82 would not be an outlier, but wouldn't 42 would be an outlier? And out of the blue, they have a question down here, which is, what is the variance? What is the variance?
Wouldn't you just square the standard deviation?
Right? I mean, they kind of sneaked up on you with that one because it wasn't a question you would be expecting to meet in this question, right? But variance is always going to be the square of the standard deviation, right? So you're either going to know the standard deviation or you'll have used your TI-84 and found it, right? So the variance is just square that number and you are good to go. And they have all sorts of different stories based on this. This one here is about the number of hours that I believe students sleep on average, which is 7.4, and a standard deviation of 1.4, and then you can figure out what number of hours sleep in each of those three categories. So that would be 7.4, add and subtract 1 standard deviation, add and subtract 2, add and subtract 3. In fact, that add and subtract thing pretty much follows all of these questions.
So is there any kind of like special rounding rules or only when it's been told in the question?
Yeah, I think the numbers are fixed, so you don't need to worry. If you treble something and it's a fixed value, it's not needed. You won't need to round it off.
Okay, because like in the example that you gave earlier, you know, yeah, the mean was 14
Yeah.
and then the standard deviation was 6.71. So if you're
Yeah.
trying to like subtract that, like, is there, I
Yeah.
just didn't know.
You would need to look at the question. If they did that, they would say to 1 decimal place or
Oh, okay.
or to the nearest integer or whatever. Now, in question 9, suppose head circumferences of adult males, adult men, are bell-shaped. Okay, some guys have big heads, some guys have little heads, but if you measure their circumferences, they look like that, right? Some are very big, some are not so big, right? And the mean is 55, and the standard deviation is 3. Okay. A 49 centimeter head circumference would or would not be unusual. Okay, let me take those numbers and show you how I would deal with them. They're basically asking you, is 49 an outlier? Right. When they say is something unusual, they're really talking about connected to how unlikely something is. So I'm going to write down the number here, which is the mean, which is what, 55. And I'll put in the standard deviation here, which is 3. Okay. And now I'm going to go and I'm going to draw a rather messy picture. I'm going to draw a usual straight line, and right in the middle, I'm going to do 55, and I'm going to go 1, 2, 3 standard deviations. So that's going to be 58, that's going to be 61, and that guy there is, I believe, going to be 64. And then I'm going to go 1, 2, 3 on this side, and that's going to get me 52, and this guy is going to get me 49, and lastly this guy here is going to get me 46. And I'm going to draw, as best I can at least, a bell shape. And right in the middle is that guy, and I'm going to put, like I'm cutting it up into pieces of cake, like that. Now, this diagram's going to get messy because there's a lot of things to be written inside it. If you take the middle and you go 1 standard deviation either side, you get 68% of the data. Agreed? So 68% are in that range, right? 1 standard deviation. Now, this piece and that piece are meant to be the same shape. So I'm going to split it and call those 2 pieces 34. So it's a bit like I'm going to take a cake and cut it into bits so I can tell you what the pieces are. Now the next one's going to get messier. 2 standard deviations is 95%. Agreed? 2 standard deviations. So from 49 to 61, from here to here, it's 95%. Now, why is it going to get ugly? If you take 95% and you split it into 2 equal halves, so there's half on this side and half on that side, you get 47.5%. Now that means these two pieces are 47.5, and these two pieces are 47.5. Since this piece is already 34, if I take away 34 from this guy, I knew I've got, check that out, 13.5% belongs here, and 13.5% goes here. This picture that I'm building is pretty much the same picture for all of these questions. The only thing will change is the scales on the bottom. These two are going to be 34s. These are going to be 39s. Now, if you go all the way to the end, right, from here to here, 3 standard deviations, you get 99.7%. And you can imagine it's split equally. So if you divide it by 2, you get 40, well, you get 0.3, so 49.85 on each end. And if you add these two and take that away, basically you've got the piece that goes here. So let's see, I have 49.85. I'm going to take away 32. And I'm also going to take away 13.5. Let's see what that looks like. Take away 5, gone. It's 0.8, 5, that's 4. I have 4.8%. Let me check, that looks a bit on the small side. No, okay. 5, 8, 4, yeah, we're good. And then you split it into 2, so 2.4%, 2.4%. And then there's a tiny little piece left over on either side. And I know that this is 99.7, so that's 0.3% split equally. And so right at the end, you get half of 0.3, which is 0.15%. And over here, half of 0.3, 0.15%. Now, all that hard work was just for this question. Explain whether or not it would be unusual to have 49 centimeters head circumference, right? If you look at 49, it's here. So what percentage of people would you expect to be in that range, or smaller? 2.4, that guy. These two pieces add up to 2.55%. Now I'm going to put in the key. Hopefully I didn't screw up there on my calculation. Kind of feels a little bit out, but that's just me. I've lost the question. Yeah, it's about right. They say 2.5, but that's pretty much the same number. Now, once you've built this table, or this diagram, you can answer all sorts of questions. For instance, if I went and said to you, what percentage of people were 61 or less? Well, there's 61. 61 or less would be add up all those things. If I said to you what percentage of people had a height of 58 or more, there's 58, add up these three guys. I'll try and make a better version of that table for you and maybe put it online so we can use it for the future, but it'll kind of do for right now. So I want to finish today with one last idea, and that is a thing called the Z-score. Sometimes called, its full title is Standardized Z-score. Now, if any of you ever in the future do an SAT test, do some kind of standardized test, and the word standardized is in its name, it's almost invariably going to be using Z-scores as part of the process. So why do we need this standardized Z-score, or Z-score for short? Here's a little story. Mary and John. Now, both of them take English, but they get different teachers. And Mary got 85% in her final exam, and John got 80%. And Mary was saying to John, I did better than you. I got 85, you only got 80, nah, right? The kind of things that siblings do, right? Now, if that was the only information that we've got, I think we'd have to accept that Mary's score was higher in the final than John's, so she did do better. But let's put some reality into it. Mary was in a class where the average score that students got was 80, and that the standard deviation in that class was 5. John was in a class where the average was 70 and the standard deviation was 5. Now, we'll make the assumption that all other things remain the same. In other words, the people that were in Mary's class were just as intelligent as the people in John's class. Now you might say to yourself, Mary was in a class where the teacher was pretty lenient with the grades. In other words, it was easy to get, or easier to get an 85 in her class. Would you agree? Average is 80, 85. John, on the other hand, was in a class where the teacher was much stricter in the grading. I don't know if this is true, but students in the past have told me that they had professors who never ever gave a perfect score. And their argument was, nothing is perfect. There is no such thing as a perfect essay. There is no such thing as a perfect, report. So they always, that professor would always give them 95 or 97, right, instead of a full 100. Right? And other professors in that same situation might well have gave 100, right? So it's possible, right? So what we want to do now is compare these two scores in a fair way, and not kind of just argue about, yeah, well, that's hard, or no, this isn't, that's not that hard. And the way they came up with it is a thing called the Z-score. And what the Z-score does is it takes into account your score, the average, and the standard deviation, and it reduces it to what's called the Z-score. And the Z-score is the data, that's what you got, take away the mean, divided by the standard deviation. So let's see what the two Z-scores are. Whoever gets the larger Z-score actually did best. So Mary, let's see what her Z-score is. She got 85, the average was 80, and the standard deviation is 5, and she got a Z-score of 1. John, he got a Z-score, and he got a Z-score, well, his score was 80 as well. Take away 70, divided by 5, and he got a 2. So according to this standardized way of marking their grades, isn't it fairer now that John, even although numerically his score was less than Mary, wasn't it much more difficult for someone in John's class to get an 80 than it would be in Mary's? So John actually did better. And that's how you can standardize things over two different groups so that you essentially eliminate teacher bias, right? So if one teacher is very strict and one isn't, you can standardize their scores. SAT scores, for instance, are standardized because some years the exam that you take might have been a little bit harder than the previous year or a little bit easier than the previous year. So they use the Z-score technique to fix that problem, right? Standardize it. And so the score that you got would be exactly equivalent to anyone else's, no matter how hard or easy the test would be, because they adjust it accordingly. Any questions before we go? Because we're going to call this, the end of today. Okay, last name for attendance, although it looks like some of you already figured that out. And see you. Again, it's going to be online because I'm really not 100% yet. And bye-bye for now. I'll hang about if there's any questions.
Thank you.
You're welcome.
Yes, sir, I got a question for you.
Yes, James.
So I did the first homework assignment, the one we were reviewing at the beginning of the class.
Yeah.
And number 20, I couldn't find the answer, and I tapped out all my attempts.
Okay. Right, let me find yours right now, James. Here we go. Do it on scores. You said question 20 from what section?
From the
Numerical
first homework.
summaries. Okay.
Yeah.
Numerical summaries. Okay, I can see that because there's something missing on one of them. Let's find out. And you're right. Last question, question 20.
Because my first
Okay.
answer to that was 19.
Right. Let me show you their answer. Maybe if you can see what they were wanting, it will make more sense to you.
Okay.
Hit the right button. Here we go. Can you see this is your distribution, right?
Mm-hmm.
And if you're trying to do the mean, not the mode, but the mean would be round about the middle-ish. So if I was a guessing person, I would guess 7, maybe 8. It would be one of those two numbers. You see, that's right in the middle. Now, your answer of 1 is over here. I don't see 1 as being a candidate for the mean.
No, I was trying to retype 19 and I accidentally hit submit.
Right, so I'm wondering what 19 isn't here either, unless you were just adding up all the rectangles and it came to 19.
So I added up, so I used the information tab, and then, for example, it says the answer was 5 8 times and 6
yeah,
3 times.
I gotcha. Yeah.
So I added
Now,
all those up and then divided
what-
by the number.
Now the number you divide by is important. You might say, oh, I only divide by 1, 2, 3, 4, 5, 6, 7 rectangles, right?
Right.
But you don't divide by 7. You actually divide by the total frequencies. So there's 8 of these, and there's 3 of them, and 3 of them, and 3 of them. So that's 8, 11, 14, 17, 18, 19, 20. So you divide by 20 if you did it correctly. So your multiplication is okay, but the number in the bottom is the total number of people, not the total number of numbers. Right? There was 20 people here. Just some of them happened to use the same number.
I understand why I messed up there. Because I like I said, I got answer 19, and I couldn't figure it out. So, but that makes more sense. I'm gonna go back and take a look at that one, see if I can get that answer of 7.
7. Yeah,
Okay.
that's what you want.
All right, thank you, sir.
You're welcome. Bye-bye for now.
Bye-bye.
I was
William?
wondering.
Mhm.
I was wondering for the empirical rule with the
Yes.
68%, 95%.
99.7 guy, yeah.
Yep. What those percents were based on?
They are empirical, just means it's been done through experience and through experiments. So
So it's like the average of all the bell shapes.
When they've looked at bell shapes and they looked at enough of them, this 68, 95, 99.7, give or take a little wiggle room, came out as being pretty consistent throughout all data sets. Remarkably so.
It's like an estimate.
It's an estimate, empirical, but it's a pretty good estimate because it tends to hold water. If you use it in a normal kind of bell-shaped data, and you get an answer, let's say the answer is 68% of the data is between 42 and 49.
Yep.
If you went to the original data and you did how many people were in that range, you probably won't get 68 unless you're really lucky, but you might get 69 or 67.2%, and it's close enough to be practical and usable.
All right, that makes sense. Thank you.
Okay.